Hello again, folks. Today we're going to be talking about exponential and logarithmic modeling, right, which is basically taking the basic shape of a formula or an equation that is exponential or logarithmic naturally, and applying it to some application, like radioactivity, say, for example. These are the models that are in section 3.5. And I'm going to give you an example of what the graphs actually look like. But let me talk about it as we go through it. There is actually also, let me mention at the beginning here, there is some word problems that I'm going to walk you through. One looks like this. It's about population growth. And another, though you can see through the paper, is carbon dating. Try to print this out and then we'll go through it later. Right now we'll get the tools out of the way first. So, the model that we will use for exponential growth, well, it has several features, so I'm going to try to draw this in different colors to kind of emphasize. Let's see. It's going to have actually the variable y and the variable x, but the x will be an exponent if it's an exponential, so I'm going to put that up here, all right? The other key features that are to look out for are the coefficient that would be in front of the exponent, which will be here, but also the base of the exponent would be e here. And sometimes also there is a coefficient of the exponent here. So y equals a times e to the bx, is what you would see. That's the model. In terms of the graph, you already really know what this would look like. Holding some markers. I'll draw the picture here. All right. It is a curve. That famously goes through the point 0, 1, and has an asymptote along the x-axis. Right, so a point that, a boundary that it will never reach, and a curve like this. Okay. That's the basic shape. Right. Technically, at the point of 1, the coordinate would be 1 and then e being 2.71, whatever it is, into infinity, something like that. But of course it could be transformed and the graph will change slightly. But that's the basic shape, right, for something that is exponential. Right? A curve upward like that, it's growth for that reason. Right? On the flip side, if we just alter this ever so slightly, use a darker marker here. Nothing better than a darker marker. Has all the same features, really. Base e, and potentially a coefficient here, except one extra thing. All right. It could have a negative exponent. Right. In terms of the function graph, that would look something like this instead. All right, you'll still have an asymptote running in theory along the x-axis, and barring some major alterations, right, you might have just the graph curving down like this. Right? Now I should mention, really, it's a specific case for each of these. The graph here, right, would be the bare bones incarnation of this. Y equals e to the x and nothing else. Right? But it is a positive x. Right? And it is based upon e, the number e. Right? Similarly here, if this is not too fancy, just e to the negative x, that's as complicated a picture as you'll get. The others, save this, come back to that. The others are logistic, right? And the model looks something like this. This is pretty involved here. And I don't use that one. I wish my markers wrote with the same consistency each for, you know, the same color, but they don't. Anyhow, imagine now that you had the input variable of x, right? But it is now part of the denominator, and there's still the coefficient, a value of 1 here, and a b value here as the base, and then another coefficient of r, which I'm going to squeak in here. Perhaps I should just do this instead. Make that blue. And make this green. Not super important, but the sign here would be negative, so be mindful of that. Okay, this would be the model for logistic. Now, as far as the graph is concerned, it's pretty interesting. It looks something like this. It has 2 asymptotes. An asymptote that is more or less the normal thing running along the x-axis, and then an asymptote based upon whatever the a is usually here, running parallel. Right? So if this was, say, 3 here, right, then it would be at the location of 3. Here, as an example, y is equal to 3 over 1 plus e to the negative 5x, something like that. Okay. If you have a 3 here, here's your asymptote, it would seem. And the actual curve looks like this. It's interesting because it's different from anything else we've seen. There is this exponential increase and then it levels off. So something like this, more or less a kind of a very stylized S shape. Right? There's a word for that actually, it's called sigmoidal. A sigmoidal curve. Where it starts to grow and then it levels off. Right, hence this asymptote, the maximum. Okay. Gaussians look like this. Here we go again. Let's see. Coefficient of base e, and it will in fact be a negative, but this has a complicated exponent. The exponent will look like this. Constant, and then x minus another coefficient here, constant, squared. And the graph will look something like this. Sorry. If you had, as an example of this model, you might have something like this. A slimmed down version of it. E to the negative x squared. Right, and this is famously the bell curve. For obvious reasons, right? It curves like a bell. Okay. Statistics uses this a lot, or some derivative of it. As for the logarithmic, purely logarithmic, there's those that are based on natural log, base e, and those that are based upon common log, which is a base 10. Right? Remember that. If it's natural, it's base e, and common is base 10. Right, so, as for an equation, you'd see something like this. It's too faint. Keep popping up. No problem. Y equals plus. Trying to squeak in the common features first. A. The coefficient of B. And then I'm probably getting myself in trouble here, but in this instance, natural log, which as you know is ln for natural log. A little bit squeezed in here. There you go. And then of course x, because you need an argument. And in the common sense, it would be, instead of ln, it's log of x. We'll just kind of separate these two. Here's what the graphs would look like in both cases. They're very similar, but they're not exactly the same. A log graph, and this is going to be too faint. Be careful. Has a vertical asymptote through the y-axis, and in its most basic form would be something like this. A curve running this way, and similarly a little bit flatter version of this running this way for the common log. As an example, if you had, again, the slimmed down version of this, let's just say hypothetically you had y is equal to 1 plus the natural log of x. There's an interesting point, 1 it goes through, in addition to, again, having a vertical asymptote like that. And a slimmed down version of this, 1 plus log, of x. Again, we'd go through the same point, 1. Just be a little bit flatter. It's hard to exaggerate on this, but you get the point. I get the point. Waka waka. Boo hiss. Anyhow, so let's say something about each of these for the sake of distinguishing them. All right. The logs have vertical asymptotes. Virtually everything else has horizontal asymptotes. In the case of Logistic, it has 2. Right? Let's see. Where do you use these? Well, these two, this one, exponential growth, and exponential decay, are really the things that you are responsible for, at least judging by the textbook assignments. You would need to know these two, in addition to compounded interest, which is something that we discussed in section 3.1, right? So that formula you can go back to. These other ones exist, but whoever decided what the assignments were did not go into these. The bell curve is what you would use in statistics. Let's see. This logistic growth model is something that involves, like, say, growing bacteria in a laboratory. You may start out with having the bacteria all fine and dandy, producing more and more of themselves under ideal conditions. In other words, they're being fed, they're getting sunlight or whatever, and then suddenly stop. Right? And they'll level off, as their population would level off as a result of that. This is bacteria in, say, a lab. You know. The Gaussian curve is something that you would use in statistics of some sort, like the SATs, for example. Let's see. And let me get into the other things. Let's see. Okay. Oh, as far as logarithmic is concerned, like the Richter scale, like in the subject of seismology, you know, earthquakes, you might see some incarnation of the logarithmic model. Anyhow, the examples that I'm going to show you now pertain to exponential growth and exponential decay. And I really want to start with decay first, if that's right. Just like decay. All right. That's an overview. All right, now if you would, let's take a look at this. Carbon dating. I'm going to walk you through that. I'll have to read this, unfortunately, so I hope you'll humor me. Right. I did write this, but nonetheless. Carbon dating. All right. When an organism dies, the total amount of carbon-12, which is stable, non-radioactive carbon atoms, in its body remains fixed, while the total amount of carbon-14, which is naturally radioactive, just continues to decay over time without replenishment from some food source, because naturally if something is dead, it doesn't eat. So it can't acquire more carbon-14 as a result of ingesting it. Right? Normally, that is to say when something is alive, the ratio of carbon-14 to carbon-12, that is radioactive carbon to non-radioactive carbon, is 1 to a trillion, which is 10 to the 12th. Let's see, to estimate the age of a fossil, right, by a number of years since it died, the scientists use a formula based upon exponential decay, this model, all right, and basically compare what is to what should be, i.e. the fossil's ratio of carbons, right, that is normal, 1 to 10 trillion, well, that is unique to the fossil, like it might have something different than that, I should say. I'm double talking, but the fossil's ratio of carbon, which is unique to the fossil, right, to the amount that is the normal amount, 1 to a trillion, right, and they specifically use this formula, right, what you see here, R equals 1 to 10 to the 12th times base E, and the exponent is negative t for time over 8,223, right. All right, given that information, estimate the age of a newly discovered fossil for which the ratio of carbon-14 to carbon-12 is R equals 1 to 10 to the 13th, which is 1 to 10 trillion, right, 13 zeros. Right. Now, as far as going through the process, I'm going to do it, it's these steps. Right. And I'll erase the little bit that I need to. Some background information. in case this comes up. As for reading element symbols, reading the symbol for an element let me just give you some fun facts here. That's a little too faint. Put that one away. Alright, here's more or less a model to follow in and of itself. And then there's the example in hand. At hand. Okay. Let's see. The abbreviation for the elements, and there is the xenon is the only thing that is X, but it would be X is E. Let's just say the element name would be an abbreviation according to some capital letter usually, or a capital letter and then a lowercase letter. Xenon gas, I want to say, is X and then lowercase e, but there's no X. Right? And there's two numbers that you would read. Right? There is a number that is referred to as the mass number, sitting in superscript, and then immediately below it, the atomic number. Now, what are they? Right? The atomic number, whatever is sitting here in subscript, that's the number of protons. And protons basically identify the element. Right? So, for example, carbon is 6, right, on the periodic table. That's its atomic number. Right? It only has 6 protons, right, compared to other things. The mass number, on the other hand, is the combination of the number of protons and neutrons. So, if protons are the thing that basically identifies the element, and 6 being what makes carbon, you could still have a larger mass number than 6, right? It's usually 12, I want to say this is carbon 12, right? Which means it has 6 neutrons, coincidentally. But the number of neutrons doesn't matter. It could have more neutrons, and in theory it could have less neutrons, however common that may be. Right? What makes something radioactive is basically having more than the usual amount. So if 12 is basically the normal amount for carbon, its mass number. Right. If it had 13 instead, that means it has an extra neutron than would be normal. Right? And in theory, that neutron, if it's separated from the atom, right, could cause a reaction. Right? Sort of like playing pool. Right? If you can imagine a nucleus as being sort of like a pack of billiard balls, and you fire the cue ball into the pack, what does it do? It splits the pack, all right? That's what happens in a nuclear reaction. It is a fission reaction anyway. A neutron or some other particle would basically be flying off and colliding with the nuclei of other atoms and causing them to break and spread, all right? Anyhow, this is stable carbon. 6 protons, which identifies it as a carbon, and 12 protons and neutrons total. So if you see anything, especially in the homework, that they're asking you to read elemental symbols, right? Just understand that the top number is neutrons included. Okay. You had in theory, let's just say this, 14, right, as the mass number, and 6 still is protons. That's what identifies something as carbon. This would be radioactive carbon. Right, there's a phrase for that. Right, something, different derivatives of the same element. These are isotopes, right, of carbon. There's more or less the normal one, and then there's the radioactive ones, right? I suppose 13 mass number is possible as well. Anyhow, there's that phrase. No, isotopes are different incarnations of the same element. Different masses, different mass numbers of the same element. Okay. All right. Now, if you, knowing that, right, and that we're basically going to take the normal ratio of 1 to 1,000,000,000,000, right, and more or less plug that into some version of the exponential decay model, right, we can then compare that value to radioactive examples. So let me erase a little bit here. This is the formula that you are given. R equals 1 over 10 to the 12th, that's 1 over 1,000,000,000,000, so a very minuscule amount, times e to the negative t over 8,223. Right. I would say that number 8,223 is potentially the half-life, which is how long it takes for the mass of something radioactive to reduce in mass by the amount of half, right? That's so many years, right? 8,223 years. That's probably the half-life of carbon-14 specifically. Right? I'm taking an educated guess, right? Or making an educated guess, right? Anyhow, this is the formula that's given, right? If I were to follow my own logic here, let's start with this. If you just were reading this amount in blue here, right? Estimate the age of a newly discovered fossil for which the ratio of carbon-14 to carbon-12 is 1 to 10 trillion, right? Identify the appropriate model, right? If you're talking about radioactive substances, the model that would be pertinent, all right, would be exponential decay. I'm just going to sort of write this directly above the formula that is actually given. So, and I'll put it in the same colors that I had it. Picking up that one. Wish I didn't. Because I want to compare these purposely. Compare the model to the given formula to translate the variables. Let's look for what's the same. So far, the only truly obvious thing that is the same is that it's a base E, right? So we don't have to worry about that. That is consistently the same thing. I mean, if you wanted to put in the number 2.71, you could. I wouldn't, right? But it is possible. You don't need to mess with that. What we have here is a difference when it comes to the input variables and the output variables, right? And for the one that is a little bit more obvious is this one that's sitting on the left of the equals. Instead of calling the output y, right, we're calling the output r, which I can only guess is r for ratio. Right. Anyhow, just understand that basically r is standing in for y, right? It's the output. Right. Let's identify what the input variable is. In this case, right, the input variable is a little disguised, right? It's actually t, right? These are the input variables, right? Normally it's x, right? Just to relate it back to a graph, right, which is usually labeled x by y, you know, x axis and y axis. But instead, because this is an application, we're going to call it t, as in time. Right? It is still nonetheless sitting in that position. Now, I know that there is this sort of denominator that is here, right? But what you could assume then, since this negative and this x show up essentially here and here, is that the b value in this case is 1 over 8,223. The coefficient of x is basically a fraction. All right, and again, I'm speculating a bit, but I want to say that that is the half-life of carbon-14. Right? How long it takes basically in terms of years for the mass to reduce to half of what it was originally is the half-life. All right. Anyhow, 1 over 8,223. And then the last thing is this, all right? The coefficient of the base E is this ratio, all right? 1 to 10 to the 12th power, all right? Which is, again, 1 to a trillion, 12 zeros, 1 and then 12 zeros. Okay, now, if I do the next thing, all right, substitute the given value. That's what I'm going to basically put in here. The quoted value for the radioactive substance that is what this fossil is comprised of is 1 over 10 to the 13th power, right? That will go in place of r here, right? This substance has this ratio, right? This is the fossil, right? And there's still this, 1 over 10 to the 12th. There's still E. There's still this, 8,223. Okay. That's the only thing that we could do as far as substituting into the formula that's given, right? Not to belabor the point, but again, I think it is a good habit to compare the models that we have with the unique application of the model so that you can identify what the inputs and outputs actually are, because there's lots of variables, right? It's a literal equation. Okay. All right. Now, anyhow, how to go about actually solving this, right? The question is to estimate the age of the fossil, right? Which basically means you want to know what t is, you want to know what time is, you want to know how many years, right? Presumably the fossil is, right? How old it is. That means that you have to solve for t. If you're going to solve for t, look where t is located, right? This is the actual variable that we're looking to solve for, right? It's part of an exponent, right? Which means that we have to somehow bring it down to the normal tier rather than leave it where it is. And the way that we would go about doing that, as I mentioned on the sheet here, is this, right? You're going to employ the natural log at some point, maybe not immediately, but at some point. So let's do that. I'll put this over here. Use natural log. I may erase this because I don't need it anymore. Okay, I'll do the work adjacent here. Right. If I took the natural log of 1 over 10 to the 13th, no, don't do that yet. Define myself. What I should do is, I am going to use the natural log, but to do this appropriately, to solve for t, all right, isolate e first. Okay. Which means I have to move this fraction from where it is to the opposite side. Okay. I hate writing over here, but I really must. I'm going to use a blue that actually writes nicely. That's good. Alright, if I have 1 over 10 to the 13th and 1 over 10 to the 12th, all these features attached to it, right? And it is understood that these are being multiplied, because this is a coefficient. I'm just basically going to try to move this over here. How do I justify moving a fraction? You multiply by its reciprocal, right? It really is the opposite of multiplying, which is dividing, but you know that when you divide fractions, you end up flipping one of the fractions. So the bottom line is, if I want to move this fraction from where it is to the opposite side for the objective of isolating this, right, then I'm going to have to multiply by its reciprocal, which is that, 10 to the 12th on top. And like normal, or as usual, if I did that here, I'm obligated to do that here. And there's going to naturally be a cancellation effect, because even if I have something enormous, like 10 to the 12th is again a trillion, right? It's something essentially divided by itself on this side. To multiply a fraction by its reciprocal is to divide by itself. That will cancel to 1, and that will just leave me with this, which is really what I was after. E, isolated, right? These two things I can now straighten out here. Let's see. All right. That leaves me with this. 10 to the 12th sitting on top of 10 to the 13th. Okay. Now, taking advantage of the quotient rule for exponents, I can simplify exponents that have the, or powers that have the same bases, right? This is a base 10, this is a base 10, and according to the quotient rule, in theory I would subtract these, and I end up getting a negative, unfortunately, but that's just the way it is. I'm going to put the work up here. 12 minus 13 would leave me with 10 to the negative first. Right. If you like, and I'm automatically sticking that above the line. If you feel more comfortable with exponents at this point and you know that basically the outcome here is going to end up as a denominator, that's fine. All right. But if you feel a little sketchy about where to put the outcome of this work, you are never going to be wrong if you automatically stick it above the line with its appropriate sign, because if it's 12 minus 13, that's negative 1. You could always adjust it later, right? I'm going to leave it alone for right now. All right? And then on this side, I have what was left over here, which is this 8223. All right, now finally, the other part of this is that I'm going to use the natural log. All right, both sides. All right. I really want to do it here because I want to basically move the position of t to get it on the normal level. All right? But if I do use natural log here, remember, just as anything you do, like moving this coefficient from the right side to the left side, you have to be consistent. So if I applied natural log here, I'm obligated to do it to the opposite side. All right? The effect is then this. The natural log of e, these are inverses, right? And the result of that is that you would produce the amount of 1, right? Simultaneously, the exponent that is attached according to the power rule would be moved down in front as though it were a coefficient, right? Just to point at the reason I can get away with this. A while back, you had a handout that looks like this. Basically what I'm doing is a couple of different things. I'm acknowledging that to take the log of something, right, where the bases are the same here and here. I know that natural log isn't written in this style, but it would be log with a base e. Right, to take the natural log of something that is a base e to begin with would give you basically the result of 1. Now, if it happens to have an exponent, that would be the outcome. The exponent would be on more or less the normal tier. You can kind of think about it in terms of the power rule, right? If you have an exponent sitting here next to the inside guts of the argument, it becomes a coefficient. Right? That's basically inverses and the power rule in tandem is what's going on here. Anyhow, the natural log of e is 1, all right? If this is the exponent, right, the exponent would in theory be now adjacent to that 1 here. And meanwhile, on the opposite side, it's still natural log of 10 to the negative 1. I'm running out of space, so what I'm going to do is erase a little bit over here. And continue with my work. I have this preference personally, it doesn't really matter, all right, where I like to have the variable on the left side of equals, right? My writing the problem like this instead, just understand, is not really performing algebra so much as it's me being a twit. You know, I just can't stand not to have my variable on the left side of the equals. Makes me more happy. I guess because of the conditioning that we're all brought up with, right? Where they say, what's the objective, kid, when you're learning to solve equations? The objective in its most how shall I say? In its most literal sense is this letter equals this number. So that's why I like to have the letter on the left. Not that it has to be that way. Anyhow, this is not performing any algebra here. This is just me being anal retentive. Okay. All right. Now the last thing is this. Let me just put this back. I don't have to do more papers. To move the denominator here, 8,223. Again, if you're trying to isolate the variable at this point, you are dividing on this side to justify moving it from the left side to the right side, or whatever you prefer. Perform the opposite operation. The opposite of dividing by 8,223 is to multiply by 8,223. And there's the nice balancing act that is algebra once again. If I did it here, right, then I'm obligated to do it there exactly the same way. You can get away with murder in math as long as you're consistent that way. And you know what I could have done as well, move the negative. I'll do that now. Right. If again, just to be anal retentive, I like to have the coefficient in the front. Then the last thing that I could do is simply, you know, divide by -1 technically. Or just acknowledge, well, t would have to be negative 8,223 times the natural log of either you could just write it as 10 to the -1, or to just conform to good etiquette, put it in fraction form rather than negative exponents. This is the same as this. All right, anyhow, we're done, except that we want to get a meaningful number, which is, for humans, usually a decimal. So we're going to use our calculator now. But we're going to basically enter this into our calculator. T, which represents time in years, is equal to this quantity. Negative 8,223 times the natural log of 1/10. And I'll enter this very carefully. All right. You see my calculator. I'm going to clear out whatever was there. Clear. If you're going to use a negative, remember to press this button here. Negative, not the minus. 8,223. Going to be very twitty and put it, no, not twitty enough. Precise, I should say. Times the natural log here, right? And then the argument. I'm going to be fancy, right? You could just put 1 division 10 and be done with it, right? I'd like to put it in the more intuitive way, which is to enter it in the style of a fraction. So there you see an obvious top and an obvious bottom. 1/10. Close the parentheses to be a good guy. This is good to go. Negative 8,223 times the natural log. Enter. 18,934.15722. So just shy of 19,000 years. Just terrible. You know? Time is approximately, if I rounded it to the nearest year, and I didn't really specify, it would be 18,934 years, approximately. Right. That's how long it would take. Well, pardon me, that's how old the fossil is. Age of the fossil. Right. We didn't really have to take half-life into consideration. It was in the formula. All right. And you really generally don't have to worry about that. All right. Just manipulating the equation is really the point of the exercise here. All right. So that's interesting, right? A fossil is almost 19,000 years old, right? And how is that determined? Just by comparing how much radioactive substance it has, right, to what is normal. There, not to sidetrack, but there was recently a video that I had come across on, I think it was in my news feed, right, on Facebook, and they were saying that they were having trouble with the carbon dating of some Viking skeletons, basically, and it had something to do with their diet. They apparently, because they were seafaring people, the Vikings, right, they had a diet heavy in fish, right. So the radiological substance in fish is somehow different than that which is in land-dwelling creatures. And it was skewing basically their data. It was making the age of the Vikings, or whatever this army was of dead soldiers that they uncovered, it made them seem older than they actually were. All right. Anyhow, that's a more recent development, and it's interesting, I think. This technique still works, right? As long as you know that there isn't some other weird situation involved here, right? Like, you know, the dietary habits of Vikings. How strange that is. All right, let's see. I want to show you something else. I put it on the bottom, falling apart here. I put it on the bottom of the same piece of paper, which is to explore the graphical method to go about this process. What we have done here is basically explore an algebraic method for solving this problem. Right. I'll summarize that with a diagram. Solve this problem, I went about it in a process that would best be described as algebraic method. Right. Just using the symbols, just using properties of logarithms, just using old techniques. Right. Alternatively, what we could do is try a graphical method. Provided that you have, the textbook keeps saying, a graphing utility, right? Which means, yeah, you can go on the internet and use whatever software you want. You can just use Google search engine and it will graph a lot of things for you. Or go to some specific website. If you happen to have a TI-83 or 84, right, you might go about it this way, right? The trick to this is basically to take your equation, right, and whatever is sitting on one side of the equals, just refer to it as y1. And whatever is sitting on the opposite side of equals, just refer to it as y2, right? All right, and graph these independently. Right? And then look for the point of intersection. Here's what I mean. If this was our equation to start with, R equals 1 over 10 to the 12th times e to the negative t over 8,223. And then I substituted this much. I put 1 over 10 to the 13th in here. This is still all of the same information. Right. What you would do is a couple of things. Right. Let's look for the equal sign, start smack in the middle here. There's a break in my board here, you can see. Let's just call these two separate equations. We'll call this, although it's a terrible number, it's 10 trillion, we'll call this an equation that I'm going to graph onto itself. And then I'll call this other half a second equation, second y equals, onto itself. And then enter them basically into the calculator and superimpose the pictures and then look where they cross, right? The point of intersection is the answer, right? Just realize, or anticipate what you're going to get. This, even if it's ugly, right? This is a puny little number, right? Because it's 10 trillion as a denominator, right? It's still a constant. I guess that was offended that I said that. This is still a constant, which means that this side of the equation is going to be a horizontal line, this side of the equation is going to be an exponential curve, right? It's going to be exponential decay, which means that in terms of a graph, we should see something that looks like this. Right? A horizontal line coming into contact with an exponential decay. And that means that wherever they cross, that should be the answer for all intents and purposes. Now, truth be told, because we're dealing with such tiny numbers, there are limitations. The calculator may unfortunately, resist our effort. Right, but we'll see what we can do. There's more than one way to skin a cat, for lack of a nicer expression, because that's disturbing. All right, here's what I would do. All right, let me point at a couple of things. All right, we're going to put the equations, these two halves, separately. All right, in y equals. That's the first thing. Okay, so as long as they're cleared out, that's fine. All right, because I tried this already, right, and it kept giving me error messages. I finally got a little frustrated with my calculator, and I said, hey, you know what? I reminded myself, there's two options here. There's, if you will, for analogy, the automatic, zoom, and the manual transmission, Windows, right? No matter which way I tried the automatic, and there are a lot of options in here, a good bet is if it's not Z standard, then it's zoom fit, right? It just wouldn't work. So what I finally did was, you know what? I'm gonna try the manual transmission instead. So here's what I'm gonna have you do, all right? Just to circumvent any issue. Go to Window, right? And in Window, you can force the dimensions of the screen to conform to the unique problem. Right? Sometimes that's the best route, is to just not even bother with the automatic, because it just doesn't understand what the user is getting at. Right? So what you would do is this. Let's change the dimensions of the x and y axis. That's what the minimum and the maximum here is for x. Right? The graph that we're going to get is basically what quadrant? Well, out of 4 quadrants, this is really quadrant 1. Right? So what we need to do is establish maybe a maximum for the y value and the maximum for the x value. The minimum of both will be 0. So for x min, I'm just going to put 0. All right. For x max, all right, we kind of have a vague idea already that this is going to be a large amount of time. I don't mean like 1 year, 2 years, 3 years. It's like 20,000 years. All right. So let's make the since x is being filled in by t. All right, this is part of the reason why I was bothering you before about deciding which is the input variable and which is the output variable. In the model, x is the input variable typically, right? And in the application, t is standing in place of x. Almost looks like an x, right? Hand gestures. This is math voodoo, if you will. So that means that the x-axis is really the t-axis, and that really represents time. So I'm going to, in place of x maximum, I'm going to put the time maximum. We already know that it's 18,000, 19,000 years. So maybe make it 20, right? Just make it ever so much, a little bit higher. So I'll put 20 in here. And if I have to go back and adjust it again later, I will, right? 20,000. All right. The scale, I'm just going to leave it as 1. Y minimum, 0 also. Y maximum. All right. Let's see. Well, the y values are a really, really tiny number, right? This is a little bit hard at this point, right? If in theory we have a horizontal line that is at this really puny number, 1/10 trillionth, right? It's 0.000000000, really tiny number, right? Then the y maximum should not be too far away from that. I don't even know if I would use whole number 1, right? I might use something that is on the magnitude of, 10 to a certain power. So something slightly larger than 10 to the 13th would perhaps be 10 to the 12th, right? All right. So let me try that first. So I'm going to enter 10 caret, and then I'll put, I don't know, 15 or something. Oh wait, I gotta do it as a fraction. So here, I'm gonna enter this that as the maximum. Now I know it's a little counterintuitive, right? You think 12 is a smaller number than 13, and go, oh well, that's got to be the smaller amount. Remember, it's a denominator, all right? So if you have a large denominator, that really represents a puny number, and the larger the denominator, that is the higher the degree here. All right, the even punier that it is. So what I'm going to enter here for the y maximum is 10 to the, we'll make it negative 12th. And if I have to go back and tinker with it, I will. 10 to the negative 12th, all right? Because it's 1 over 10 to the 12th. I'm just using negative exponents to represent the fraction. You could enter a fraction if you want. Okay, I'm going to leave the scale alone. Right, now, if I hit graph, I didn't enter the formulas yet, but you'll see that it's just quadrant 1, basically, that we're looking at here. This is the t, otherwise known as x-axis. This is the y-axis. That is the r-axis in this context. Right. Now I'm going to finally do this. I'm going to enter those values. As I mentioned before, this is a little bit darker, perhaps. No, wrong one. I got 2 blacks, and I keep picking up the one that doesn't write. All right, this one to make it perfectly visible, or better at least. I'm going to type that in the location of y1. Okay. So again, if you want to be fancy, right? You could hit 1/10 to the 13th, or you could do it in the more intuitive fashion, which is like this. That's numerator, denominator. The numerator is 1. The denominator is 10 to the 13th. Okay, I'm going to scroll out of there. And that is to verify, yep. That's going to be a constant. It's going to be, again, a really puny number, but it's a constant. So it's going to be, and since it's y, it's going to be a horizontal value, just ever so slightly higher than the x-axis. Right? So if x-axis is really y equals 0, this is slightly bigger than that. So it'll be ever so slightly above it. Let me hit graph. Right? There's the line. That is the horizontal line. Okay. I'm going to go back, and in y2, I'm going to enter the more complex model here. Which again, to make it a little bit more easy to read, y2 is going to be this ratio of 10 to the 12th times e to the negative t over 8,223. And that has probably is the half-life of carbon-14. Okay. I would be very anal retentive about how you enter this, because again, there's always some syntax error, and you think you've done something wrong when you really haven't really. It's just that the calculator doesn't understand what you're talking about. So be careful. I'm going to start with anal retentively. This is overkill, isolating the coefficient, all right? And then I'll enter this again in the intuitive fashion. Right? Incidentally, if you're using an emulator rather than an actual physical calculator like this, dumb it down. Right? What I mean by that is that when I tested my own emulator of Texas Instrument Calculator software, it had limitations. It was nice, right? It's a great emulator, the Emu Wabbit, or Wabbit Emu emulator for this calculator, but it does seem to have limitations, so dumb it down a little bit. In other words, just use / for division rather than maybe this fancy thing here. Okay, I like things to be intuitive, so I'm going to enter it like this. Okay, scoot out of here. Right. What I've entered so far is just a coefficient. Right? Notice that's very similar to the constant, right? Because this is the normal situation, 1 to a trillion. This is the fossil, right? 1 to 10 to the 13th, 10 trillion. Times, again, this is overkill, but I'm being very careful to circumvent a syntax error. So now I'm going to hit second, and then you'll notice E, that comes into frame here. There we go. This is behind natural log is E. And now I have it as an exponent here. I'm going to put that in here. Again, I'm going to be careful. So I'm going to put negative, and then I'm going to put a parentheses. Again, if this is maybe a little bit silly. And now I'm stuck with, in the model it is of course t. The calculator doesn't understand this variable is just changed label. So I'm just going to call it x, which means I'm going to use this button here. All right? And now, just to get it over with, I'm going to hit division rather than the fancy way of writing, and type what I presume is the half-life, 8,223, and close the parentheses. If there is an error, and I don't know, it may happen, I'm just going to go back and simplify around decimals if I have to. All right. Again, if the emulator gives you trouble, put it in the decimal equivalent. It's just not sophisticated enough to handle a number this puny. All right. So you may have to round. All right, let me just verify that that looks correct. I think that's fine. All right. I'm going to hit graph, cross your fingers, hold your breath. There we go. All right. Rock and roll. And it crosses. Now, it's just on the edge of the screen here. All right. Because remember, I gave it a maximum of 20,000. It appears to work. And it probably could get away with it. If you ever had an error message where it didn't draw, but you really didn't do anything again, you know what that means half the time? It means that you have to just change the dimension of the screen ever so slightly longer. All right, here's what I mean. If you went back to the manual here, and instead of 20,000, you just made this ever so slightly larger, I don't know, 25,000, all right? It might make the picture a little bit better, right? If it doesn't draw, if it gives you an error, again, it just means that it's outside the scope of the screen. There you go. That's a little bit more satisfying because you see it actually crosses, right? So now here's what you can do. If you hit trace, right, you see this is the first equation, the constant, right? 1e means 10 times 10 is the base. It's a goofy way of writing it. If you move the arrow up, it moves to the other function. Then you can toggle back and forth. You could just scoot along to the point of intersection, right? The smarter thing to do would be, once you've hit trace, is to tell the calculator to tell you what the point of intersection is, right? So here's what you would do. Behind trace, there's the calc feature. So you would hit second and then trace, right? And then you notice these options. We'll come back and do value later for a different problem, but intersect is option 5. It's going to ask you some goofy questions. It's going to, is this the first curve? Whether the thing is curved literally or not, that is the question that it's going to ask you. No, it's a straight line. But you're going to go, yeah, okay. So you're going to go, yeah, that's right. All right, and it's going to go, is this the second curve? And you're going to go, yeah. All right, just go along with it. All right, and then you go, you want me to guess? And you're like, yeah, I do. All right, and then you hit enter a third time, and then it goes, boop, that's the point of intersection. 18,934.127, right, or 157, right, I'm reading it backwards. All right, that's years. All right, since x is really representing t, and t really represents years, time, all right, that's the age of the thing. The point of intersection is the answer, all right? It's tedious, but I'm going through the intricacies of it because I don't want you to make a mistake. Anyhow, just trust yourself that you can make the thing do what you want it to, all right, if you're stubborn enough. All right? Okay, it's just an option. You could use the graphical method. It will come in handy, I assume, at one point in your life. All right. Now, let's do the other problem, which is the back of this page, population growth. Right? And you'll have to humor me again because I'm going to have to read it. All right? Sometimes the exponential model needed is given, as it was in the last problem. Right? And indeed, sometimes you have to find it yourself. That's really the point of this exercise. It's figuring out how to get the equation more or less from scratch. Right? Now, the example I used here is stolen from the book I wrote in blue. Right? A population of fruit flies increases according to the model of exponential growth. And since it says that, you kind of know which one of the original five, I guess it was technically 6, all right, models to choose from is the exponential growth model. A population of fruit flies increases according to the model of exponential growth. After 2 days, there are 100 flies. And after 4 days, there are 300 flies. How many flies will there be after 5 days? You can make a prediction if you have the mathematical model. So here's what I wanted to do. The first step logically is, if you didn't know, right, identify the appropriate model. So I'm going to play a little dumb, even though I'm the guy who wrote this. I'm not playing, right? I'm being myself. But I want to sort of walk you through the process, so humor me. Step 1, all right, put your glasses on correctly, all right? This is step 1, I'll label it, population growth, and faint marker. Bothers me. I don't even want to look at it. Sorry, I'm being anal retentive again. Population growth of fruit flies. Help me! Help me! I don't know if you ever saw The Fly. It was an old sci-fi. I don't mean the one from the 80s, well, that was pretty cool. I mean the one in the 50s. It's kind of special. It's a famous line with it. Alright. Identify the model. Very faintly. Alright. It is appropriately exponential growth for population growth, because usually things that are organisms grow. They can be unfortunately killed off, that would be decay. All right, but here's the model. Y equals a to the e of bx. Okay. Number 2. That's still faint, yes. Compare the model to the description. I should say compare the model in the description. Compare the model to the description, all right, to the description to translate the variables. This is kind of an awkwardly phrased sentence, which is my fault. Anyhow, I drew this table. We don't have an equation, again, to really directly compare variables yet. Right? We'll get to it. Right? But I did draw this table because I wanted to sort of help it along. Kind of squeaking that in. Now remember, if the model is any indication, there's an input and there's an output, as though it were a little machine. All right, so I'm going to start with that. We'll figure out what the input is and then what the output is. All right, the input under normal circumstances is X. The output under normal circumstances is Y. That's the way it is in the model. All right. In this situation, we're talking about a certain number of days that is quoted to us, 2 days, 4 days, and then they ask about 5 days, right? And then they ask, and then it refers to or correlates to a certain number of flies. So if we could translate what is normally the situation to what is in context here. All right, let's use the appropriate abbreviation, or something that at least implies, all right, the thing that, the flies. Implies the flies, all right? Which would you say is the input, all right? The time that it takes, as in the case of the decay model from the last problem, or the flies? Is that the amount that is that the number that you're going to insert in order to do a calculation to spit out a value? If you're looking for flies, then flies has to be the output. So let's maybe use F for flies, right? What is the input that it's basically dependent upon, right, is time once again. But it's time in a different increment. If the time for radioactivity was years, right, the time here is days. So you might use D, right? It doesn't really matter, but if it makes it more clear to the person writing the model, I would go with what is intuitive in terms of variable, right? D for days, F for flies, right? Otherwise, T for time and N for number of flies. Right. And then there is some data points that I'll mention to you. I labeled this as data 1 and data 2, and they went data way. All right, so in the context of the problem, all right, again, if I've decided that D is the input, D is in days is the input, the first amount of days that are quoted is 2 days, all right, and then the amount of flies that correlates to is what, 100, right? Yes. So we have that and that. Okay. Then the second day is 4, and then it says that it went up drastically. It went up 300 flies, right? Fruit flies, little red flies. They like bananas, I know, because they're always eating mine. God's creatures, you know. Anyhow, if you want, you could make another column for 5, but we don't have the actual value yet, so I would kind of resist the temptation to do that for right now. Anyhow, the reason that I'm establishing this table is because I want to get you sort of jazzed to be in the habit of going, okay, I'm going to basically decide what the inputs are, what the outputs are, all right, and then make labels, right? Now, this is going to be, if you're going to do this by hand, just realize again, there is something that you could make a calculator do almost the same thing. I'll do it both ways. All right. Here's the procedure for doing it by hand. I've outlined here, right, from step 3 down. Okay. All right. First things first. I'm going to basically take the model that is established already, and the goal here is that we're going to tweak it so that it is unique to this particular application, unique to this particular problem. I'm going to basically write this twice. because in order to proceed, I have to basically input the data points here in the first one, and input the data points here in the second one, and then rearrange this and stuff it in that, right? In essence. Alright, just to kind of give this a little context as outside in terms of math at least. There is something known as a system of equations. In the case of a system of equations, you have different techniques. This is one of them really, without specifying it, called substitution method. When you insert one equation out of the system into a second equation in the system, right? Normally what it looks like is that you see an equation with two variables sitting on top of a second equation with two variables. Sometimes they draw a fancy brace next to it, like a little sort of math sandwich. Anyhow, more than one equation considered in tandem is referred to as a system. You don't really need to know that, but I just want you to understand there's a background logic to this. All right? We're going to essentially solve a system, right, via substitution. And substitution is basically sticking one equation, or at least half of it, into the other one. Anyhow, back to the work here. I'm going to insert data points in place of x and in place of y. All right. So I'm going to stick 2 here in place of x and 100 here in place of y. Okay. Notice what's left over as a result of doing that. E is E. It doesn't have to change. It's a number. It's a famous superstar of math, right? 2.71 into whatever it is into infinity. But these two variables, A and B, those are the things that we need to figure out. So what we're going to do is we're going to basically rearrange this to solve for A. All right, which is not too complicated. I mean, it really just entails moving the exponent E from this side over to the opposite side. It's going to be ugly looking, right? But this is the way it ends up, right? If I divide by E here with its exponents, that would cancel. And if I did it here, I'm obligated to do it to the opposite side, so B to the B2. All right, that means that A is equal to this. 100 sitting on top of E to the 2B if I write it in better etiquette. Okay, the coefficient of 2 in the front. All right. Now, that is temporarily. All that we know about A, and it's sufficient. Because simultaneously what we're going to do is take data set 2 here and put them in the appropriate places. 4 would be standing in place of x here, and y would be 300 here. All right. I'm going to now substitute what A is into this equation, because what that will enable me to do is basically solve for B. I will eventually get an actual number, right? So if I will have 300 is equal to this value of 100 over E to the 2B, and sitting next to it is still this, E to the 4B, just to conform to a better etiquette. That is the coefficient up in front. Now I could pull tricks. All right. For one thing, I could more or less slide this base E underneath its counterpart here, and then take advantage of the quotient rule for exponents, which is to subtract the actual exponents of 4b and 2b. Okay. What I'm getting at is this. If I just sort of slide this over to here, so that this is understood as being 2b sitting underneath 4b, okay, then according to the quotient rule, this is going to subtract these, and since they're like terms, they're both b's, you're just going to end up with 2b, right, is the end result. That means that this is really 300 is equal to 100 times e to the 2b. Okay. Now, similar to the last problem, right? I'm going to employ natural log in order to solve for b at some point, but not yet. What I'm going to do is I'm going to isolate e by moving the 100. So if I divide by 100 here, that'll cancel here, and then I'll divide by 100 here, and this will simplify down to just 3. Right. Because I'm running out of space, I'll put this up here. So this is really 3 is equal to e to the 2b, and now at this point it would be probably ideal to apply natural log. Right? Just remember, when you apply natural log, you have to be consistent as though opposite operations, right? Whatever you do to one side, do to the opposite side. Right? The natural log of 3 is whatever number. I think I want to say it's a decimal number, but what does that amount to? It means that the natural log of e here, this is just 1, right? And what was the exponent will be in the front, right? If you're looking for some justification, natural log is base e. When you have the same bases, a base e is the argument and the base of the function, right? They're inverses, so they basically are just 1. At the same time, the power rule, just to explain this, these are inverses and they produce 1. And then according to the power rule, whatever you have as the exponent here, that becomes the coefficient. So just because, again, I'm manual retentive, I like to have the letter on the left side. I'm just going to write natural log of 3 over here. Okay, that means that this is really just 1 times 2b is 2b. Natural log of 3, divide by 2. And that is a decimal number, right? What I would do just to preserve infinity, I'm being a math purist right now. All right, I'm going to leave it, wow, I have a possum. And he's sneaking off. I don't want to move the camera, but there's this cute little possum in my backyard here. And anyhow, I'm like a dog, cat, you know. All right, anyhow, to preserve the infinity of this, potentially, I'm just going to leave it as this expression, right? That is an actual number, right? All right, now, as far as our model is concerned, what we have is this. Y is equal to a times e to the bx, right? Well, we just figured out what b is. B is the natural log of 3 sitting on top of 2, all right? That means that there is one other thing that we need to find, a, all right? How do we do that, all right? Well, we already have a formula for that, right? So what we can do is basically insert the same value here, right? And then we'll reduce it a little bit, right? And then whatever simplified incarnation we end up with, insert it there in place of a as the constant, the coefficient, same difference. All right. So I don't want to erase this table yet, which is why I keep sort of working around it. But here, I'll put this information underneath. Remember what I said. This is the temporary answer that we had for A, but now we know what B is. So in place of B here, I'm going to put the natural log of 3 sitting on top of 2. Since there happens to be a 2 here in the formula, or there's something on the formula that I have here, these tools will cancel. Okay. All right. To sort of show you the intricacies of E and the natural log, there's something going on here. Right? 100 is 100. Right? But E that has an exponent that is a natural log is really this. A natural log, abbreviated ln, is really a log with a base e. Once again, when you have these same bases here, they're inverses, and the result is that you're just going to get 3 here. It's like saying, I don't want to drive you nuts, but just to point at the rules, right? It's more or less this situation here. Inverse property 2, where you have a base, though it's being blocked out by the light behind me. See, the base here is whatever letter it is. I didn't write E, but it's a base. And then there's the logarithm with the same exact base. The outcome is whatever the argument is. So if the argument is 3, then the outcome is 3. Okay, so that means that this is really what number? A is really 100 sitting on top of 3, which is, again, this is a number. Strictly, right? It would be 33.3 into infinity, right? Again, to preserve the infinity, I'm being a math purist. Math purists don't like to round, right? I'm going to insert this expression, right? Here. 100 over 3. So to write it a little bit more cleanly, because that is pretty sloppy. All right. This is our formula. Y equals 100 over 3 times E to the natural log of 3 over 2 times x. All right, which is pretty interesting, right? And we could probably reduce that even further still, all right, for the same reason we could reduce this. All right. I'm going to resist the temptation to do that in a moment. Anyhow, the other thing I would do is go back to the table here and fill in the appropriate labels as we had decided. So D is what is standing in place of X, and F, which is number of flies, is standing in place of Y. That means that whatever I insert in place of the number of days and perform this calculation, it will spit out an F value. Okay. Let's type it. All right. I'm going to clear out of here. All right. Again, I'm going to be very super careful, and I'm going to use the appropriate syntax. I'm going to enter it first, and then I'll show you what I got because it's a little hard to do it backwards. Trying to write this the most intuitive way. Okay, this is as it would look if I just had put the variable x here. All right. I'm going to answer the question now because it asks how many flies should there be after 5 days. If this is where D is supposed to be, I'm going to put a 5 here instead of an x. 5. So that should be it. Again, this is probably overkill, but this is the formula in its most explicitly written, hopefully clear fashion. All right. So if there is an error message that occurs, and I'm just going to, because we're dealing with very tiny numbers and maybe the calculator can't handle that, I'm going to slim it down. I'll round if I have to. There it goes. 519.6. All right, that's the number of flies, which is on the magnitude of what we might have expected, right? If at 2 days it was 100 flies and in 4 days it was 300, then apparently at 5 days it was about 520, if you want to round, something like that, 520 flies. Okay. Let me just double check something. That is the correct answer. I'm just interested in maybe if I can simplify this. Let's see. According to the same property. Let's see. The base e to a natural log, in theory, it would be 3/2, I would say. 100. Do it again. I'm deleting stuff. Let's see, 22. No, it wouldn't work actually. It doesn't work. I think because it has the, because of this denominator, it's screwing everything up here. Yeah, it doesn't give you the right answer. Alright, Basta la vida, leave it alone. Alright. I was trying to pull the trick from over here before, but it's not exactly quite as pure. There is basically a denominator of 2 in this case, and that when I try to simplify it to just 3 sitting on top of 2 and then check the calculation, I get a different number. I get 50 rather than 520 roughly. So you can't, if you have a denominator here, you can't pull that property apparently. Right. Anyhow, let me show you what you could do with your calculator to get the same answer. We did again, we went through the process algebraically, all right? And it is invaluable, that skill, all right? But, all right, what's nice is to have software, right, that could not only draw a nice clean picture, but then verify that the formula that we've constructed is correct, right? So, I want to save this, right? And I probably should write it a little bit nicer. And now I want to show you what you could do with this, right, when armed with the right tools. So let me erase the little that I can. I did write the instructions just above, or just below the problem, right? But basically, if you wanted your calculator to draw a graph from data points rather than drawing a graph from an equation, right? You can, right? And it's basically this. You would have, this is really what you would do in statistics class all the time, all right? To input data, all right, you're going to press the stat button and then click, and you can enter edit. And then you'll see that there are lists. List 1, list 2, list 3, whatever. Let's just say that X is L1 and that Y is L2. Right. We don't have a lot of data, so it's not too complicated, but here you go. All right. Hit stat, edit, and now you see some data points. Right, I already took the liberty of entering these. Here's 2, because again, if L1 is X, and I have 2 X's. I have 2 and I have 4. And one of my Y's, 100 and 300. Well, I gotta edit this. Yeah, that's good. Okay, here's my Y's and L2, 100, 300. All right. Now, if you want to draw a picture based upon the graph here, right? A couple of things I would do up front. I'm going to clear out this other stuff because I don't want it overlapping. So clear. All right. If you hit second and then y equals, you'll notice that there is written in blue here, stat plot. Stat plot is basically graphing options for the data that you enter. There's a bunch of blanks here. I'm going to start with 1. When you go into it, it is preset to be off. And L1 it's understood as being your x values, and L2 is understood as being your y values. You can change these if you want, all right? If you wanted to, for whatever reason, notice that behind here in blue, behind the regular digits 1, 2, 3, you see L1, L2. You'd have to hit second and then change it. We don't want to. What's more important is the type of graph. There's bar charts, box and whisker plots, and this is a scatter plot, which is what we want. First of all, I really should turn it on. Right? And now I'm going to choose the type of dot. So I like this one. It's the most obvious little block. All right, now if I hit graph, you're not going to see too fancy a picture. You're just going to see 2 coordinates, 2 pairs. Right? If you don't get a picture, it's because I had messed with the screen. So now I'm going to go back to zoom. All right? Here's zoom, and I'm going to go to zoom stat, which if you scroll down the list here, is this option here. All right, now you see that it's giving me these 2 points. I want to back off a little bit, so I'm going to hit zoom out, and you see there's a slightly better picture here. All right. All right. Okay. All right. Now, the truth is that people would have the calculator do the hard part of crafting this for them, and there's really nothing wrong with that. There is a way to go about doing that. But what I want to do instead, because I think it's kind of satisfying, is I want to now go into y equals, right, and enter this unique function, right, and see if it overlaps appropriately. If it does, then it's the correct equation. I already know that it is anyhow, but I want to show you that. So what I'm going to do is, now that I have a picture, and you can move the cursor around if you want, I'm going to go back into y equals and now type this complicated ugly gobbledygook here. So I'm going to be very careful and a little bit more fast than I had been. All right. Let's see. 0.5. Natural log of 3. And then there is one little alteration I have to make. Because the calculator does not understand that the labels are F and D, y equals is already understood, but I'm going to change this back to X when I'm entering it. So I've gotten to the point where I have half of the natural log, that's 0.5, because I'm being lazy. All right, and now I'm going to put, close the parentheses perhaps. There you go. And now I'm going to put X. All right, and if all goes well, all right, it should draw the picture. Okay. And you see, climbing through the points. Isn't that lovely? Only 2 data points is what I needed. All right, so I figured it out. All right, and you can. All right, isn't that great? I know that's not something to just jump for joy for, but it makes me so happy, you know. And they're like, oh, look, I mean, I can get my calculator to do something practical. I can mathematically model, all right, with very limited data, as long as I know what the appropriate type is. So, like, a lot of times when we're doing something, it's just a linear sort of relationship, but exponential is a much more interesting thing. Okay? So, that's that. Now, as far as getting it to tell you the answer as before, right? There's a couple of things you can do. You could establish a line of x equals 5, right? And then, which would be a vertical line. There is a way to do that. And look for the point of intersection, but what would be more appropriate is, again, to engage your features here in your calculator, right? If you hit trace, right, you could scoot the cursor over to where you estimate is increment 5. 1, 2, 3, 4, 5, which would be about here. And then go up to that point. And it's a little stubborn. It's resisting me. Okay. If it won't let you, Like one thing I think is going to happen, if I type, even though I hit trace and under normal circumstances it wouldn't be a problem to just enter 5, it's giving me trouble, all right? There's a way around that, all right? Here's what you do. I'm going to go back to the graph, all right? I'm going to purposely engage second and then trace calc features behind it. And now I'm going to elect the value, all right? Function. Now it understands, even though it should have before. Just when you use stat plot rather than regular graphing, just that, it gets a little confused. So I'm going to enter 5, right? And it's going to tell me what the equivalent F value is, or Y. 519.6, right? About 520, all right, as estimated before, right? And it's precise, and it's exact, all right? Well, I shouldn't say that. There's a rounded decimal here, but it's very precise, right? So more than one way to go about the process. Now, if you didn't feel like going through the trouble of this calculation, there is a function in your calculator that it might be more trouble than it's worth, but it's called Exponential Regression. And it's basically getting the calculator to give you this as close as it possibly can. All right, normally in a statistics class they would do that. All right, I'll just show you how to go through the process. Let me quit. If you hit stat, again, let me play that. If you hit stat and you go over to where it says calc, as long as the software is up to date, if you scroll down here, you'll see that you have linear regression, that's logarithmic, exponential. Let me see what linear does. That's logarithmic. I'm not in love with it. Yeah, don't do that. Okay. Yeah. The option that this most closely resembles is EXP-reg. That's exponential regression. Again, not to jump the gun here, but you have other options in here. Linear regression is y equals mx plus b, as a model for, predicting what the data ought to be of some, application. But in this case, we know it's exponential. So I'm going to go for this. Right? If you elect this, right, because there is no other data in the calculator, it'll automatically give you something, right? But if you had to specify, right, here's what you would do. You would tell it which lists to draw information from. So I can press enter right now and it's not going to give me an issue, but if you had more stuff in the calculator, be more specific. So I'm going to hit second and then 1, and you notice that it's going to say L1. That is telling the function the x values are in L1, all right? And then you hit a comma, and then you tell it the x values are in L2, right? Now there is one other thing you can do. You could tell the calculator to take the equation and stuff it in y equals so that it graphs the same curve that I had done a minute ago. I don't want to do that, but if you were going to go through the process, all right, let me show you. If you hit, let's see, I'm reading it backwards again. See, it says vase here. If I should probably hit comma first. Hit vase, and then choose y vase, and then you say function, all right? If you hit enter here, and then choose a specific y, I'm gonna go with y2 because I use y1, all right? Enter. That's telling it to tell you what the formula is using these data sets, x1 and, the x values and the y values, and then write that equation in y2 specifically under y equals. Now here's what will happen if you press your enter. It'll give you this information. It will tell you what the coefficient A is, which is 33.3 repeating, so with certain precision. That's 100 divided by 3. All right. The only problem is that it has to round it because it has a decimal. then it's telling you what the base is. Now in this case, the base is 1.732, whatever it is, right? It didn't write E, right? Because it's basically using the outcome, right? If E, the way I have it calculated is this, 3/2, and there's an X here. I want to say that what is filling in this value here on the calculator screen is what is B. They're calling it B. And there's still an X adjacent to it, right? The outcome of e to the natural log of 3, I should put that 2 in, so it's just 3 here and 2 there, right? That should be the decimal that it's approximating. So if you see in this case, it's 1.732, whatever it is. I'll just write it here for reference. All right. And then these other things here that it says r squared and r equals 1. That's how reliable I want to say that the function is. This is something that you would worry about in statistics. Right now, you just want to see that, okay, this is the model. Y equals a times an exponent, a power of some base to a certain exponent, right? This is the actual thing, right? This is telling you without typing in the actual numbers what those values A and B ought to equate to, right? Now, if you look in y equals, here's what it wrote, all right? To a very high degree of precision, I'll scroll down here, all of this, right? All right. What I'm going to do is I'm going to erase mine, and just to show you that it graphed without you having to actually type something. All right. I'm going to erase mine that I calculated, even though I'm very proud of it. All right. And now the only thing that is in here is just what the calculator itself decided was the appropriate function. My glasses keep slipping off my face. All right. So now I'm going to go back to graph. And there's our 2 data points, and now it's filling in its own line that it calculated. And notice it is exactly the same thing. All right. I'm sorry, I'm moving around when I shouldn't. But look, isn't that lovely? All right. I felt like Marvin the Martian, right? Isn't that lovely? It is. All right. I'm going to destroy your planet. Anyhow. I think that's fantastic, but hey, you know, I'm a simple man. I wanted to show you something here. Not to beat a dead horse, but again, the e to the natural log of 3, 2. Yeah, I'm going to type it. 0.5 times the natural log of 3. Close this. Right. That's 0.5 is 1/2 as a coefficient rather than as a denominator, but it's the same difference. Natural log of 3 and is the decimal really of 1.73205, right? The only downside to having the calculator do the work for you is that if you're not really familiar with what's happening here, you may not realize that that really is what the base is. It's giving you the decimal equivalent rather than the actual function. Right? No biggie, right? I mean, like, and again, in the statistics class, you probably wouldn't care, all right? But we math purists, we like E, you know? So E is cool, all right? All right. So that's enough of that, all right? You've seen how to do these problems a number of different ways. So let me leave it at that then. Okay, for homework, really you just work on section 3.5, right? Do the problems that are listed in the syllabus. Next week will be the last regular class that we have, in which case it's just going to be Appendix 5, A5 is how it's labeled. All right, and then that's it. The week after that would technically be the final. All right, I'm still kind of waiting from on high from somebody to say, hey, do this or that in terms of the final. I have my own idea of what I'm going to do, and I think you'll be happy But I'll be more specific, I promise, right, as soon as I know I'm allowed to. Okay, so for right now, because you want the experience, and that's the most important thing, you know. Try the textbook problems that pertain to section 3.5. Okay, all right. I'll see you guys on Sunday next week. Take care.